In this set of notes, we're going to look at exponential growth and decay, and this section corresponds with section 2.1 of the textbook. It is recommended to also read that section of the textbook. So we're going to start by looking at modeling population growth in discrete time. And so we're going to start by considering the chain of transmission of a virus. And suppose that each infected person infects 2 new people every 7 days. And so here we've got kind of a diagram to illustrate what that would look like. We've got our first person here, and then notice within 7 days they are going to infect 2 new people. And then after another 7 days, each of them are going to infect 2 new people. And then after another 7 days, each of them are going to infect another 2 new people, and that process is going to continue. So here below we have the exact same image, but what I've done is I've got some horizontal bars so we can kind of look at those different points in time. So starting off here, notice in the first, this blue horizontal bar, this is what we would call day 0. So at the very beginning there was only 1 infected person. Then after a week we've had 7 days have passed, and we have 2 new infections. And then after another week we have 14 days, and notice now we have 4 new infections, since each of the people after day 7 infect 2 more, and this process continues on. So notice that we can summarize this information in a table. So at day 0 we have 1 new infection. Then after 7 days we have 2 new infections. After 14 days we have 4 new infections, and notice that this process is going to continue. And we don't have to stop the table here. Notice that this could just keep on going. All right. Now notice here that our units are in days, and so they're incrementally increasing by 7. And so often what we'll do is we'll convert this to a new time unit just to make it easier to write a general formula. So here I'm going to rewrite the table, but I'm going to let 1 unit be equal to 7 days. And so whatever the increase is, or the spacing between these, that's what you would set your unit to be. And so notice, in order for this to work, these would need to be evenly spaced. So here, instead of looking at days in the second table, we're going to look at weeks. So at week 0, we'll still have 1 new infection. Now at week 1, we're still going to have 2 new infections. And week, that should be at 2. We'll have 4 new infections, and so on. So notice that the number of infections is not changing. All we've done is convert days to a new unit, which is in weeks, and by doing that our time now just increases by 1 with each row in the table. And so converting to this new time unit, what it does is it's going to make it easier for us to write out a general formula for the number of new infections at time t. And so notice t here is going to be time, and so again ideally we'd like time, or t, to just increase by 1 at each iteration. And so we can denote capital NT as the number of new infections, or population size, at time t. And so you'll notice throughout this chapter we're going to refer to population size. This is in a little bit of different context than probably what you're used to in your biostats course, and so just do keep that in mind. And so again, this is going to be at time t, where t is measured in the new time units. So in other words, we want these units where t just increases by 1 each time. And so by doing this, we can write the following. So we're going to write a function. We're going to use capital N to denote that function. And usually when we write out a function, when you see the parentheses next to the letter which denotes the function, what this means is N is a function of t. So in other words, the population size is going to be a function of t. Or even another way to put it is the time point we're at is going to determine what the population size is. And this is going to be equal to 2 to the power of t, where t could take the values 0, 1, 2, and so on. So where does this piece, the 2 to the t, come from? Well, let's go back to our table and see. So let's start out here. I'm just going to kind of draw a new line here and see how these values are developing. So first, we started with the number 1. Now notice to get 2, what we did was we doubled 1, or in other words, we multiplied 1 by 2. To get 4, we doubled the number of new infections from the previous time step, or in other words, we doubled 2, which is the same as multiplying what was in the previous line by 2. And notice that this trend continues. So for each new line, I take what was in the previous line and I multiply by 2. We can use exponents to help us write this out. So notice that 1 is equal to 2 to the 0. 2 is equal to 2 to the 1. We have 2 to the 2, 2 cubed, 2 to the 4th, and so on. So notice the value in the exponent here is equal to the time point we are at. And we could do that for any of these. So in other words, the population size that we derive, or the number of new infections, is a function of what time point we are at. And so that's where this equation down below is coming from. We're going to refer to this again, so I'm just going to call that equation 1. Okay. And so notice here we defined a function for all t which are non-negative integers, that is for t is equal to 0, 1, 2, and so on. And so we call this kind of function discrete. So later on in the course I'll refer to discrete functions, so this is going to be a discrete function. And what this equation does is it allows us to determine the population size at any discrete time t directly. So notice again, when we built that table, I talked about the units we want to increase by 1. So we don't have any increases that are by like a half or by 2.75. That would not be a discrete function. All right, so for instance, at time t equals 10, notice that instead of having to build out a table where I had 11 rows to get to time equal to 10, I could just directly use the function. And so at time 10, I would expect 1,024 new infections. We could also create a graph of this function. So usually when creating the graphs, we're going to put the function or the output on the y-axis, and then the variable that the function uses on the x-axis. So notice that t is going to always increase by 1, so I'm going to label my x-axis as follows. And you might ask, well, why aren't I making each of the individual tick marks the numbers? And the reason for that is just for ease of reading, so my graph isn't all smushed together on the left-hand side. And then to determine what units I want to use on nt, I can come up here and kind of get an idea looking at my table. I can see that nt is going to increase pretty fast. So here I don't want to use units of 1 on the y-axis. Instead I'm going to use units of 10. So this is just a choice that I'm making to visualize this function. There are other ways to do this. All right. So now we can use our table to help us make this plot. So notice at time 0 we had 1 new infection. So I'm going to place a dot about right there. At time 1 rather, we had 2 new infections. So at time 1 we're just a little bit further on the y-axis compared to time 0. At time 2 we had 4. At time 3, we had 8. At time 4, we had 16. At time 5, we were at 32. So notice I'm starting to increase more rapidly going in the y direction, but keeping the same amount of increase on the x-axis. At time 6, we have 64. And then by the time we hit time 7, I'm actually all the way now off my plot and up here. So kind of connecting these dots here with a line, I know this is going to look something like this. And so this function is what's called an exponential function, and the type of growth that it represents is exponential growth. And so in exponential growth, notice we start out, the growth doesn't increase very much to start with, but then very rapidly we see large increases that just continue to go up. This function is never going to come back down. It's just going to continue rapidly increasing upward. The base 2 reflects the fact the population size doubles each unit of time. And so notice we've got the 2 here. We could have other numbers there. There's no reason that we have to have a 2. There could be cases maybe where each person infects 5 new people, or 6 new people, or maybe just 1 new person. And so that would change what that 2 is. Now, often just for ease of notation, we will drop the parentheses and have the t as a subscript instead. And so that's what this would look like. And so that subscript notation is used only for discrete functions. And so we could also write it this way. Now, one thing to note is that 2 that we were just talking about, this is what we call the base number. And again, we could have a different value there instead of 2. All right, so far we've assumed that starting out we only had 1 person infected. There's no reason that we have to just start with 1 person. We could have 50 people to start with. And so let's see what that table would look like. So notice at time 0, we're going to start with 50 infections. But we're still going to double it for each unit in time. So if I double 50, notice that's going to be equal to 2. If I double 50, that's going to be equal to 100. And then at time point t2, I'm going to double what I had at time point 1. So that's going to be equal to 200. And notice this trend is going to continue. And so we can guess the general form of NT with the initial value of 50 from the table. So notice to derive these values, I did something very similar to what I did before. Here we started with 50, then we had 50 times 2, 50 times 2 times 2. Down here I would have 50 times 2 times 2 times 2 because I'm doubling each time. So notice we still have, if we look here, change my highlighter color, we still have all of those 2's that we had when we looked at the table previously. So in other words, we're still going to have the 2 to the t. The only piece that really changed was previously we had a 1 out front because we had only 1 infection to start with, whereas now we have a 50 out front. So our new general form of our formula could be NT is equal to 50 times 2 to the t. So in other words, we have our initial value out front, and then we still have that piece of the exponential function that tells us we're doubling at each time point. And so another way that we could write this is we could say that the population size is a function of t, and that function is equal to the initial population size times 2 to the t. And t could be equal to 0, 1, 2, and so on. In other words, all of those integers. And so this gives us the general formula for population growth. And so here, notice you've got NT is equal to N0 or N0. So that's your initial population time. size times r to the t. So what is the r in this case? So r is the base number. So for our formula, r was equal to 2 because we were doubling at each time point. Let's say we were tripling at each time point, then r would be equal to 3. If each person was infecting 10 new people, r would be equal to 10. And so this is also called the growth constant. In other words, it tells us how we're growing at each new iteration or each new time. When we construct the tables for a number of new infections or population size with r equal to 2 at consecutive time steps, we doubled the population size from time step to time step. In other words, we computed the population size at time t plus 1 on the basis of the population size at time t using this equation. And so what's going on with this equation? So notice, if we look over here, here is the doubling piece, that is the 2. And then the nt is the population size at time t. So in other words, the population size at t plus 1 is equal to the previous population size times 2. And so that's exactly what we did up here at the table. So notice, when I found the population size at time equals to 6, I doubled the population size at the time before that. A rule that is applied repeatedly to go from one time step to the next is called a recurrence equation or a recursion. And we say that the population size is defined recursively by that equation. So in other words, we're doubling at each time point, and so that is a recursion. And so the equation alone is not enough to completely specify the sequence. We also need to know the value of n naught. So in other words, we need to know how many people were infected initially. And so suppose we want to use the equation and the initial condition to calculate the population at size time equals t. Or probably t equals 5. So first, note the following. So we know that at time point 1, we're going to have 2 times the number of initial infections. Next, we could calculate N2. So in other words, the population size or the number of new infections at time 2. Well, notice that N2 is going to be equal to 2 times N1. But we know that N1 is equal to 2 times N0. So that's equal to 2 times N1, N0 rather, which is equal to 4 times the initial value. And so similarly, we could show the following. We could show that at the third time point, we're going to double what we had at the second time point, and that ends up being 8 times the initial value. At the fourth time point, we're going to double what we've got at the third time point, and that's going to be equal to 16 times the initial value. And at the fifth time point, we're going to double what we had at the fourth time point, so we're going to end up with 32 times N0. And so notice what this does is this gives us 2 ways to describe the population size. And this is going to be, again, for t equal to 0, 1, 2, and so on. So we could say that nt is equal to 2 to the t times the initial value, which we've seen before, but we just show that this is equivalent to n to the t plus 1 is equal to 2 times n t. Oops. And so notice the first way that we see, that is this piece right here on the right. Because notice that each of these, this is 2 to the 3 times NO, 2 to the 4 times N naught, and 2 to the 5 times N naught. And then the second way that we have here, this one right here, this is what we see here in the middle. And so more generally, we could write the following. And so remember R, all that is dictating is, are you doubling at each time point? Are you tripling? How are we increasing from time point to time point? So if NT is defined by a recurrence equation and we do not know the formula for the solution of the recurrence equation, then it can be hard to deduce the behavior of NT as t increases. So next we're going to discuss plots that we can use to understand the function NT. And your text is also going to discuss a second type of plot, and you can read about that one on your own. So the plot that we're going to look at is a plot of NT against, NT plus 1 against NT. So we're going to plot NT plus 1 on the vertical axis against NT on the horizontal axis. And so plotted this way, plotted in this way, the exponential growth equation, which we have right here, so that we just saw previously, is a straight line through the origin with slope r. And so how can we see this? First, notice that really what we have here with this equation is something that looks like equations of lines that you've seen in the past. Okay, so kind of looking at what we've got here. First of all, notice that nt plus 1 is on the y-axis. So you can think of that as being the y that you're used to. Here, on the right side, we have r times nt. The r times nt, this piece, is really your slope times your x. Because notice nt is on the x-axis, so r is the slope. So what happened to the y? This line goes through the origin. So in other words, A is going to be your y-intercept. Well, the y-intercept in this case is 0. So this equation is really the same as how you would write out a line that you've seen previously. We just have some different notation. So recall that slope is equal to rise over run. In other words, for each unit increase on the x-axis, how much y is going to change? Well, each time that we change nt by 1, we're going to see how much nt plus 1 increases. In other words, that is going to be the slope. So for example, if r is equal to 2, then the graph is going to have a slope equal to 2. And we can use the graph to calculate nt plus 1. Oops. That should be marked out. For each of the nt equal to 3, 10, and 20. And so notice here we don't actually need to know the initial condition. And so we can see that. So for here, we have the nt equals 3, the nt equals 10, and the nt equals 20. And so notice when nt is equal to 3, the next time point is going to have 6. When nt is equal to 10, the next time point is going to be equal to 20. And when nt is equal to 20, the next time point will have 40 for this example. So that's going to conclude this video for section 2.1. As always, if you have any questions, please let me know.